Okay, so let's talk a little bit about intermolecular forces. So what are intermolecular forces? Well, simply put, intermolecular forces are the attractive forces that exist between molecules. So we're looking specifically at how molecules are able to attract one another. And there's three main ways they can do this. We have London dispersion forces, dipole-dipole forces, and hydrogen bonding. Now I want to be very clear, intermolecular forces aren't bonds. So we're not looking at the sharing of electrons. We're not looking at the donation of electrons. All we're looking at with intermolecular forces is attraction between molecules. And you're going to have varying levels of strength of those attractive forces depending on the type of force that you have. So I have to admit, I'm a sucker for SpongeBob memes just because I love SpongeBob, and I felt like this was a great opportunity to throw this meme out there. So here we see the strength tier of the forces. So up here we have the virgin, weak, petulant SpongeBob, and he perfectly represents London forces because London forces also are extremely weak. They're the weakest of the intermolecular forces. Next up in sort of the mid tier, we have the Fry Games sort of athletic, determined SpongeBob. And that's good because dipole-dipole is sort of the medium level strength. So dipole-dipole forces are pretty strong, but they're not extremely strong. They're just sort of somewhere in the middle. And hydrogen bonding, we see the buff Chad ready to fight SpongeBob because hydrogen bonding is the strongest of the intermolecular forces. Hydrogen bonding is fairly strong, I would say extremely strong. It takes a lot of energy to break up things with hydrogen bonding going on. Although don't be too caught up with this term bonding, this isn't technically a bond. Like I said, none of the intermolecular forces are technically bonds. They're just associations between molecules. But we use the term bonding because it's kind of like a bond, I guess. We'll look at it later. I included ionic bonding down here with the Ultra Chad SpongeBob, just because I want you to note that covalent and ionic bonds are far stronger than these three forces. So with covalent and ionic bonding, what you see is electrons either being donated and accepted with the case of ionic bonding, or shared in terms of covalent bonding. But ionic bonding is the Mac Daddy of all the bonds, just because ionic bonding is the strongest. So it takes an incredible amount of energy to break up an ionic compound. So keep that in mind. Ionic bonds are extremely powerful. They're extremely strong. These three intermolecular forces in comparison are fairly weak, with hydrogen bonding being the strongest and London forces being the weakest. So without further ado, let's actually look at what some of these forces look like. Okay, so first up on our list is the London dispersion forces, so the weakest of them all. London dispersion forces are very weak. They require very little energy to break apart. And the thing with London forces is that they exist for all molecules. That's because London dispersion forces are just based upon movement of electrons. So all molecules have electrons moving, which means all electrons have London forces. So you'll find London forces in every single molecule you'll come across. However, London forces are the only type of force that exists for hydrocarbons. So a hydrocarbon is whenever you have a molecule consisting of just hydrogen and just carbon. And for those molecules, the only type of force they have is London forces. So all molecules have London forces, but hydrocarbons only have London forces. And so what you're going to see is the strength of your London forces is going to depend on mainly the number of electrons. So the more electrons your molecule has, the greater the London forces it has. So if you have a molecule with more electrons compared to another molecule, the one with the more electrons is going to have the higher number of, or I should say the highest level of London forces, the strongest London forces. And also molecules with better chain structures, which we'll look at in just a second. But the better your chain structure, the higher the degree of your London forces. Ultimately, though, London forces are going to be caused by temporary areas of partial positive and partial negative charges within molecules being attracted to one another. Let's see what that looks like. So what I've got here is two different methane molecules. So remember, methane is just CH4, so a carbon in the middle with 4 hydrogens coming off. And I've just got two of those molecules here, drawn in a molecular geometry type of way. And this little green guy around the molecule, the outline, represents the electron cloud. So remember that around every molecule, or at least every covalent molecule, there is an electron cloud. And that's where all the valence electrons exist. So all the valence electrons for both of these molecules are inside this green cloud surrounding the molecule. And ultimately, remember that electrons are very mobile. They're constantly moving around. So the electrons of this molecule are constantly shifting around inside of this. It's kind of like having a bunch of marbles inside of a bag. You know, you can push the marbles around inside the bag and move them around. Well, the same thing is happening with electrons inside of this electron cloud. They're just constantly moving around. So at any particular moment, the electrons could be over here, or they could be up here, or they could be over here, or they could be more evenly distributed. But the point is the electrons are moving from one area of the cloud to the other all the time. And this is going to create temporary areas where you have a more partial charge and temporary areas where you have a more negative charge. So if the electron density is higher in this part of the molecule, you're going to have a more negative charge over here. Whereas if the electron density is lower for this part of the molecule right here, your partial charge is going to be more positive. And that's going to look something like this. So for this methane molecule, the electrons are ganging up on this side of the molecule, which is why this side over here is more negative, because you have a higher concentration of electrons right here. Whereas this side of this methane molecule over here has fewer electrons, which means this side is experiencing a partial positive charge. So the partial positive charge of this side of methane molecule 1 is going to be temporarily attracted to the negative charge of this side of methane molecule 2. So the two are temporarily attracted to each other. The key word here is temporary. Because electrons are constantly moving, these partial charges on either side of this molecule are only going to exist temporarily. So 1 second they'll be attracted to each other, the next second the electrons will move, which means they won't be attracted to each other anymore. That's why ultimately London forces are so weak, because the attractions are only temporary before the electrons move back again, moving to a different part of the electron cloud, eliminating the attraction that once was here. So this attraction is based solely on the fact that at one moment in time, this molecule has more electrons on this side, and this molecule has less electrons on this side, causing the opposing charges to attract one another. That's why London forces are so weak. So here's a good example for you when you're asked to compare hydrocarbons to see which one has the greater London forces. So let's say you have this butane molecule here, and you're comparing it to this pentane molecule here. Well, first what you want to do is you want to make sure both of these have London forces. We know that all molecules have London forces, and these happen to be hydrocarbons. So we know that these two molecules are only going to have London forces. They're not going to have any other type of force. So to determine which one of these has the greater London forces, the stronger London forces, you want to use this principle right here. So we want to see which of these molecules has the greater number of electrons. Well, the pentane molecule has more atoms overall, okay? It has an additional carbon, so pentane has 5 carbons, butane only has 4 carbons, and there's some extra hydrogens here also. So because this pentane molecule has a few more atoms than the butane, it's going to have more electrons, right? Because if you have more atoms, by extension you also have more electrons. So the more electrons your molecule has, the stronger London forces it's going to have. So between this one and this one, the pentane is going to have this stronger London forces because it has more electrons going on for it. More atoms means more electrons. Okay, let's look at one more. So here we have this molecule here and this molecule here. Well, if you count the total number of atoms, both of these have the same. They're structural isomers of one another, which means they have the same number of atoms, they're just drawn differently. So we can't base it off of that because we have the equal number of electrons for both of these. So we can't judge it based on that, but what we can do is determine which of these is a better chain structure. So if you look at this guy here, okay, it's got the chain structure going on top, but it's got this additional group pointing down right here. Whereas this pentane molecule here just goes up and down, up and down. That means that this pentane is more stackable, which means another pentane molecule is easily going to fit right over top of this pentane molecule. Whereas over here, it would be pretty difficult to fit because it's not going to be a direct fit because of this extra group sticking down, right? That's going to cause those electrons to be a little further apart. Whereas over here, it fits perfectly on top of another pentane because they're both M-shaped, which means the electrons are far closer together, and that means the electrons have more contact with each other. The more contact the electrons have with each other, the greater the London forces. So ultimately, what you're looking at here is your better chain structure. The more zigzaggy your chain structure is, which basically means the more just up and down it is, the more stackable it is, the greater the strength of the London forces. Whereas this guy over here isn't quite as stackable, which means it has weaker London forces. So next up on our list is going to be dipole-dipole forces. And like we said before, dipole-dipole are sort of in the middle. They're somewhat strong, they're stronger, they're definitely stronger than London forces, but they're not quite as strong as hydrogen bonding. So they're somewhere in the middle. The thing with dipole-dipole forces is that they can only exist between polar molecules. So if your molecule is polar, it can have dipole-dipole forces. If it's not polar, it's not going to have dipole-dipole forces. So you might be asking, okay, how do I determine if my molecule is polar then? Well, to determine if your molecule is polar, the first thing you need to do is draw a good Lewis structure. Okay, so I've drawn the Lewis structure here for the molecule CH3F. We have a carbon bonded to 3 hydrogens and a fluorine. So the first thing you want to do is determine, okay, do I have any bond dipoles? So go ahead and draw all the bond dipoles for this molecule. Well, we know that carbon isn't really that electronegative. Carbon is has a very low electronegativity, versus fluorine, which has a very high electronegativity. So we know there's a bond dipole going between these two things, right? Because carbon isn't very electronegative, fluorine extremely electronegative. So now what you want to know, so draw all of your bond dipoles. In this case, we only have one. So to determine if your molecule is polar, you'll want to see if all of your bond dipoles point in the same direction. So if all of the bond dipoles in your molecule point in the same direction, then you can draw a big arrow showing the molecular polarity. So the molecular polarity is going to exist if all of your bond dipoles point in the same general direction. If they point in opposite directions, then you're not going to have a molecular dipole. So in this case, we do have a molecular dipole, which means we have a polar molecule here. That means that this CH3F molecule can participate in dipole-dipole bonding. Sorry, I should say dipole-dipole forces. So remember that when you have highly electronegative atoms, those atoms draw the electrons of that molecule towards itself. So these fluorine atoms are drawing all of the electrons in these molecules towards themselves, which means if you look at the electron cloud, you get this sort of bulge around the fluorines because they're drawing the electrons towards themselves. That means that around these fluorines, you're going to get a fairly negative partial charge, right? You're going to get a partial negative charge on these fluorines. And unlike the London forces, these aren't temporary. So these dipoles are permanent, which means that the electrons are pretty much permanently glued to this area around the fluorine, which means you get a highly negative charge around the fluorine. On the other hand, on the side of the molecule that's opposite of the fluorine, where we just have the hydrogens and carbons, back here we're going to get an overall positive partial charge because the electrons aren't really back here. The electrons are up here around the fluorine, which means the area around the hydrogen and the carbon is going to be pretty positive in comparison. So because of this, these are going to be attracted to one another, right? The negative area of the fluorine is going to be attracted to the positive area of the back end of the molecule. So that's where your dipole-dipole forces come from. The dipole is attracted to the opposite charge of the backside of the molecule. So this is a permanent relationship, or a mostly permanent relationship, versus the London forces, which were temporary. That's why dipole-dipole forces are somewhat stronger, or I should say fairly stronger than London forces, is because this dipole, this partial negative and this partial positive, are much more permanent than the temporary nature of the London forces. And this is a good example where we have the CH3F molecules participating in these dipole-dipole forces between each other. So last but certainly not least, we have the ultra-strong Chad level hydrogen bonding. Hydrogen bonding is like the Mac Daddy of them all, at least of the intermolecular forces. And that's because hydrogen bonding is got some interesting things going on with it that make it particularly strong. But there's some things that are required for a hydrogen bond to take place. So the first thing that's required is a bond donor. And a bond donor in a molecule is going to be a hydrogen that's bonded to fluorine, oxygen, or nitrogen. So if your hydrogen is bonded to an element that isn't one of these three, forget about it. It's not going to do hydrogen bonding. So you have to have a hydrogen bonded to either fluorine, oxygen, or nitrogen in order to have hydrogen bonding as a bond donor. So to have a bond donor, you also have to have a bond acceptor. And the bond acceptor is going to be a lone pair that's available on fluorine, oxygen, or nitrogen. So if your molecule has a fluorine, oxygen, or nitrogen that has a lone pair on it, that can act as a bond acceptor. And if your molecule has a hydrogen that's bonded to a fluorine, oxygen, or nitrogen, it can act as a bond donor. So let's look at this in practice. So what I've got here is I've got two different molecules. Because remember, you don't have to have the same type of molecule in order to have intermolecular forces. Intermolecular forces can exist between two different types of molecules so long as they share the same type of intermolecular force. So here we have a water molecule and a propanol molecule. The question is, can these two undergo hydrogen bonding? So if you want to see if two different molecules can have hydrogen bonding, the first thing you want to look for is your bond donor. So is there a hydrogen that's bonded to oxygen, nitrogen, or fluorine? Yeah, we have that with both of these. This hydrogen could act as a donor because it's bonded to oxygen, or this hydrogen could act as a donor, or even this hydrogen could act as a donor. So either of these three hydrogens could act as a donor because all three of these hydrogens are bonded to an oxygen. But we're going to pick on that one hydrogen in particular, so we're going to focus on this hydrogen. So let's say this hydrogen is acting as our bond donor. Now we have to look for a bond acceptor. So once you've established that you have a bond donor, then you can look for an acceptor. And so what we're looking for is on the opposite molecule, not on the same molecule, but on the opposite molecule. Is there a donor, is there an acceptor, a lone pair that can accept this hydrogen donor? And we see there's a lone pair on this oxygen. There's two lone pairs, but we'll focus on this one. So between that lone pair and this hydrogen, you're going to see the hydrogen bond take place. So this green dotted line shows you the hydrogen bond taking place between the donor hydrogen and the acceptor lone pair. And that's where that intermolecular force comes into contact. The hydrogen is drawn towards the lone pair, and that's what creates this intermolecular force. Remember, the hydrogen has a relatively positive charge, and the lone pair on the oxygen is going to have a negative charge. So the two are drawn together. But like I said, the two main things you want to look for: hydrogen that's bonded to oxygen, fluorine, and nitrogen, that's going to be your donor. Find that. If you find that, then look for your acceptor. So in the other molecule, look for a lone pair that's on oxygen, nitrogen, or fluorine. And that's how you're going to establish if two different molecules can have hydrogen bonding going on. And like I said, hydrogen bonding is the strongest of the three. It's the Chad versus the Virgin London forces. So just to recap, that's about everything. Just to recap, there are three main types of intermolecular force. There's London dispersion forces, there's dipole-dipole forces, and there's hydrogen bonding. London forces exist for all molecules, although they're particularly important with hydrocarbons. And London forces exist because of the temporary partial charges that take place when electrons move around the electron cloud. Because of those temporary positive and negative charges, you can get those London forces acting to attract different molecules temporarily. But London forces are very weak. Dipole-dipole forces is when you have two polar molecules where the negative side of one molecule is going to be attracted to the positive side of the other molecule, and they get linked together based on that. Basically like two ends of a magnet. Dipole-dipoles are quite stronger than London forces because the dipole is permanent. So that gives you that permanent sense of electron location, which allows dipole-dipoles to be stronger. And then we have hydrogen bonding, which is the strongest of the three, and that's the Chad SpongeBob, and that's the Chad force, where it's extremely strong because you have a hydrogen that's bonded to an oxygen, fluorine, or nitrogen that's going to be attracted to a lone pair that's on oxygen, nitrogen, or fluorine. And that attraction is going to cause the hydrogen bond to form, which is very, very strong, takes a lot of energy to break up. And I only included ionic bonding in this meme just to show you that ionic bonding, even though it's not an intermolecular force, ionic bonding is a bond, not an intermolecular force. It is very, very strong. Ionic bonds take a lot of energy to break up. I had this empty slot for the Ultra Chad SpongeBob, so I had to fill it with something, so I decided to put the ionic bonding in it. But just remember, this isn't part of your intermolecular forces. For those, you're just going to focus on these three, with it going from London being the weakest up to hydrogen bonding being the strongest. So there's your rundown of intermolecular forces. In a separate video, I'll actually compare some molecules, so I'll show you some good examples where I'm comparing different molecules to see which one has the stronger forces. And also in that video, I'll talk a little bit about how you can predict phase changes like boiling point, melting point, etc. based on intermolecular forces of molecules. So there you go. I'll see you then, and until then, have fun studying these intermolecular forces.